Hello everyone. So, we will continue with the electrostatic spray coating. So, today we will discuss the optimization process of the system which we have seen in last class, the fabrication of that system. So, here what we will discuss today, so effect of different process parameters. So, the different process parameters we can vary in that instrument, and those factors affect the resin weight fraction. So, how the take off of the resin, that we can vary. The effect of different parameters that I will just discuss on the resin fraction, we will see here. The process parameters are the electrostatic voltage, this we can vary. So, here the electrostatic voltage is varied from 10 kilovolt to 80 kilovolt. Then we can vary the conveying air pressure. So, in our study it has the range from 0.5 bar to 2.5 bar. Other variable is toe velocity. So, with the change in toe velocity, that is the takeoff speed, the resin content changes. So, here toe velocity was varied from 1 meter per minute to 5 meter per minute. Distance of gun from the toe, which is very important. So, that affect the again the volume fraction of the carbon fiber, that is the matrix content we can vary. Then fluidization pressure, it affect the proper formation of cloud, that also affect ultimately the resin content. So, all these factors affect the polypropylene powder deposition on the carbon toe. So, here what we have done, here we have changed one parameter at a time, keeping all other parameters constant, okay, and to investigate the amount of powder deposited on the carbon toe, and that is called resin weight fraction, and this is done by measuring the weight of the carbon toe before deposition and after deposition. That will give us the indication of the resin weight fraction. The carbon fiber, as I have mentioned, we have used the 7 micron diameter carbon fiber and cryogenically ground PP powder. So, here one parameter at a time we have varied. Now, these are the different parameters we have used. So, here in first experiment, what we have done here, powder deposition versus corona charge. So, here corona charge was varied from 30 to 80 kilovolt, and rest other parameters like fluidizing pressure, conveying air pressure, gun distance and toe velocity were kept constant level. Similarly, in the second experiment what we have done, powder deposition versus conveying air pressure. Conveying air pressure was changed from 0.5 to 2.5 bar, where the voltage, corona voltage, it is kept at 30 kilovolt and other parameters were kept constant. In the third experiment, what we have done? We have changed the fluidizing pressure from 0.5 to 1.5 bar with the voltage, here we kept 70 kilovolt and also other parameters were kept constant. Similarly, in fourth experiment, gun distance was changed from 25 to 125 millimeter, that gun distance from the toe, that distance was changed. And in fifth experiment, what we have done, it is a toe velocity was changed from 1 meter per minute to 5 meter per minute, keeping all other parameters same, where voltage was kept at 50 kilovolt. This was the setup, experimental setup. Now, the first experiment was done with voltage was changed, that corona voltage was changed, and what we have observed, with the increase in voltage, initially there is a very sharp increase in the resin weight fraction from say 0.225 to 0.4, and after that, say after reaching 50 kilovolt, it is almost stabilized. So, after 50 kilovolt, the resin fraction is stabilized, there is no further increase in the resin weight fraction. The reason behind this is that the change in the amount of polypropylene powder deposited onto unsprayed carbon toe as a function of variation in electrostatic voltage from 10 to 80 kilovolt was there, when other parameters were kept constant. So, at very low corona voltage from 10 to 20, the powder particle does not acquire any charge. So, that there is no deposition, okay, inconsistent deposition was there, there is no charge was there. So, non-charging of powder particles at low electrostatic voltage can be attributed to non-ionization of air at this voltage. Okay. So, that is why up to 20 there was no such deposition. With further increase of voltage from 30 to 50 kilovolt, the resin weight fraction is found to increase drastically, as I have mentioned, with the which can be assigned to ionization of air, okay, in the vicinity of the high voltage electrode at the nozzle exit point, and that helps in that attraction of the particles by the carbon toe. So, as soon as the powder particles move in the ionized air zone, the ionized air molecules bombard the charge to the powder particles, thereby charging them, okay, and directing them to the grounded highly conductive carbon toe. So, that will automatically deposited on the carbon toe. But with further increase, because at 50 kilovolt it has already got saturated. So, with further increase in electrostatic voltage from 60 kilovolt to 80 kilovolt, the resin weight fraction is found to be fairly consistent, there is no change. Once the powder particle reach their saturation limit as a result of increase in corona voltage, the increase in corona voltage further does not help. So, we can say around 60, 50, between 50 to 60 is the optimum, the voltage which we can use here. The next experiment is that effect of conveying air pressure on powder deposition. Here we can see as we increase the conveying air pressure from 0.5 to 1.5, there is a sharp increase in the resin deposition, but once it is more than 1.5 bar, so there is a sudden drop in the powder deposition. So, this is attributed due to the fact that the change in resin weight fraction upon varying air pressure, it is basically due to the fact that as we increase the pressure, the powder deposition is found to increase up to the 1.5 bar, and beyond that significant decrease. The increase in powder velocity leads to overcome the image force by the powder particle, which is responsible for adhering the powder particle to the grounded carbon. So, initially the powder, the conveying force was required here. So, that forces that power, the along with the voltage, the powder requires some velocity, some speed. So, with that speed the powder, that with the pressure, with that pressure the powder moves towards the carbon toe, but if we increase further beyond 1.5 bar, then it will try to overcome the image force by the powder particle. So, that here if it comes, powder comes at very high speed, high pressure, then the adhering force, it will overcome the adhering force and powder will move beyond that, will be separated. So, in addition to that, further increase in air velocity leads to falling off of the already deposited powder particle. So, if we increase the air pressure here, so already formed particles were there, and then air pressure if we increase, conveying air pressure, then already formed particle, deposited particle will get separated. So, this will effectively leads to decrease in the resin weight fraction. So, initially we need some air pressure to help in deposition, but if it is beyond certain level, here level is 1.5 bar, in that case what will happen? It will overcome the image force which helps in attraction, plus the already deposited particles would get separated. So, the falling off is actually further continues with above 2.5 bar. So, there will be shaking action beyond 2.5 bar pressure. So, there will be very less resin deposition. Okay. So, at higher pressure, due to increase in exit velocity of powder, it is observed that the pointed electrode responsible for generation of corona, it is clogged with the powder particle. So, at higher pressure it gets clogged. This clogging of electrode can affect the charge acquisition by the powder particle. So, this also it affects the charging of, if it clogs, then charging will not be proper. So, all these parameters they are responsible for reduction in resin deposition beyond certain level of conveying pressure. And our next experiment was the distance between gun point, effect of distance between gun point and gun tip and toe with the powder deposition. So, this is the toe and here it is a gun tip. So, this distance we have changed. What we have observed, initially it increases. If we reduce the distance, the deposition is reduced, and with the increase in distance, deposition increases up to say 50 millimeter, and beyond that if we further increase the distance, the resin deposition drops drastically. So, from 25 to 100 we have observed here. So, it has been reported in the literature that the electrostatic force is strongest at the short distance. Okay. So, this is the, it is strongest at lower distance. So, it was expected that the powder deposition will be maximum at closest point, say 25 millimeter. So, at that point it was expected that the charging, as the charging is maximum, so powder deposition should have been a maximum. But what we have observed at lower, if we reduce the distance from 50 mm, so gradually the deposition reduces, and where that is why we have got a contradictory result. The optimum value what we have got is 50 mm. So, as the distance is lowered from 50 mm, the weight fraction is found to decrease. At the closest setting, though the electric field is maximum, okay, it is strongest, lower powder deposition can be attributed to the size of the particle. So, at that particle, the powder that at that size lower distance, the size of particle is little bit larger. So, it has got very high inertia. At that inertia, if it strikes the toe, it will immediately bounce back, or it will not be sticking to the surface, it will reflect, because at lower distance the inertia is very high. So, powder particles 520 micron. So, at high air pressure, which imparts at higher inertia at lower distance, as I have mentioned. So, this may overcome the effect of high electric voltage. So, that is why it gives lower weight fraction in this zone. if we reduce this. But beyond certain distance like 50 mm, if we increase the distance, then the effect, that charging effect dominates. So, lower charging will be dominating and which will ultimately affect the resin deposition. So, here in this zone the reduction is due to the electric charge, and in the left zone reduction is due to the inertia. Next is the fluidizing pressure. We have changed here fluidizing pressure from 0.5 bar to 1.5 bar, and the diagram shows that it is consistently reducing initially at the lower rate, and after that it is at higher rate. The resin fraction reduces consistently. So, other parameters were kept constant. When the fluidizing pressure is kept 0, so there is no powder generation. So, powder deposition is found to be negligible. So, that is why we have not taken that part. With the increase in fluidizing pressure, powder deposition shows sharp fall, okay, in the weight fraction. The maximum powder deposition is at 0.5 bar. At a fluidizing pressure of 0.5 bar, the powder particles are set in the relative motion, which that relative motion with each other, which helps in conveying of powder and up to the toe. The set in relative motion with each other, and the fluidized bed resembles lightly boiling liquid. The density of fluidized bed is found to reduce. There is a significant increase in height of powder bed. So, that powder bed height will increase, that will affect the deposition. Okay. So, that at this condition, when the force of cohesion and gravitation between the powder particles are overcome by the upward movement of fluidizing air. So, at 0.5 bar pressure these things happen. Okay. So, this vacuum created by the flowing air which helps in sucking the powder particles. At high pressure, so 1 and 1.5 bar, the fluidization of powder particles found to be violent. So, that violent nature is not actually it is not required, and due to this violent nature the powder behaves erratically, the clogging may take place, which results in reduction in the resin weight fraction. So, for proper deposition we need proper cloud formation. Okay. It is not that the particles should move violently, there should be smooth light movement should be there. Okay. Next experiment was the effect of toe speed on powder deposition. The difference in resin weight fraction we can see with the increase in take up speed, it consistently reducing, which is basically we can be explained by the residence time. If we increase the residence time, then residence time in the chamber, this is the jet gun, powder is, if the residence time is more, that means more and more powder will get deposited on the surface. If the residence time is less, the less time will be available. So, powder deposition will be less. So, it is very simple. So, if we increase the speed, residence time is less. So, less powder will get deposited. So, it is resin weight fraction found to be decreased with the increase in velocity. The time available for powder deposition decreases. So, that is why the weight fraction reduces. So, in one factor at a time approach, so here what we have done, we have changed one parameter and kept other parameters constant. Okay. So, in this approach we have done other experiments also. So, we have changed the oven temperature and we have studied the flexural rigidity of the toe brake. So, flexural rigidity is a function of fiber volume fraction and oven temperature. So, these two parameters we have changed one at a time. So, two different fiber volume fractions were taken, 50% and 60%. So, 60% fiber volume fraction means 40% is the resin weight fraction. So, 0.4 is the resin weight fraction here, and three different oven temperatures were taken, 180 degree Celsius, 200 and 220 degree Celsius. And we have tested the flexural rigidity by Searle weighted ring yarn stiffness tester. And scanning electron microscope images were taken. This is the picture of the Searle stiffness tester, and scanning electron microscope image of the toe brake is there, it is 180 degree Celsius. You can see here the powders are not melted properly and it is not deposited evenly, but here at 200 degree Celsius these are melted, and at further if we can see it is melted, and the thickness here at 220 degree Celsius, thickness of the coating is less than 200 degree Celsius, which means that it has melted and penetrated inside the carbon fiber, carbon filament. Okay. So, effect of oven temperature on flexural rigidity, if we see, so as we have mentioned here, the scanning electron microscope picture with the fiber volume fraction 50% here. Okay. It can be seen here that for the chosen process parameters, to achieve the fiber volume fraction 50%, the temperature of 180 degrees led to inadequate melting of the particle. So, inadequate melting of the particle. So, no adherence of PP matrix to the carbon toe was observed, which led to peeling of powder from the, so it gets peeled off. We can see it is very clearly, the powder gets peeled off. So, and also the PP powder is not deposited uniformly on both sides. So, here and both sides of the carbon toe. It is not uniform because of the improper melting of the polypropylene. And in figure B, this is the figure B, which is at temperature 200 degree Celsius, powder particles melted, okay, properly, and interdiffusion of powder particles were there, which prevents it fall off. Okay. Interdiffusion is there, and at 220 degree Celsius the degree of melting is very high, and the reduction in thickness, as I have already mentioned. Okay. So, we can see here the powder deposition, its improper powder deposition is there, it is peeled off at 60% volume fraction, and at 60% volume fraction. So, fiber volume is more than more, it is severe, and at 180 degrees Celsius the effect is much more severe than 50%. At 50% the fraying of this carbon filaments were not there, but at 60% volume fraction, that means the polypropylene coating was 40%. So, at lower volume fraction of the polypropylene, it was much more severe. So, if we see the effect of oven temperature on flexural rigidity increases with the increase in oven temperature, and this is true for both 50% fiber volume fraction and 60% volume fraction. So, there is a consistent increase in flexural rigidity, okay, and both 50% and 60% we have observed. So, there is an increase at lower temperature 180 degrees Celsius, the powder particles do not melt appropriately. So, what happens if it does not melt, then there will be relative motion between the filament. So, there is no coating, proper coating. So, there is a fiber, these are the particles. So, there will be relative motion between the filaments, thereby it is not restricted, the movement is not restricted. So, toe exhibits lower flexural rigidity, but at higher temperature what happened, these particles gets melted, covered, as we have seen in the scanning electron microscope photograph, and due to this the bending rigidity, flexural rigidity increases. Okay. It further increases as the temperature goes up to 220 degree Celsius, because at that stage, in addition to the surface melting presence, the polypropylene matrix penetrates inside the carbon toe. So, that helps in enhancing the flexural rigidity. The flexural rigidity is found to be lower in case of 60% volume fraction. So, 60% volume fraction, this is the 60%, it is lower because here the polypropylene, which is responsible for enhancing the flexural rigidity, the content of polypropylene is lower. So, 60% fiber volume means 40% is PP, here 50% PP. So, due to lower quantity of polypropylene, so that here the flexural rigidity of 60% volume fraction is lower than the 50% volume fraction. After that, we have done the response surface model. So, 3 variables at a time we have used. So, it helps in understanding or mapping a region of response surface, and which ultimately helps in optimizing the parameter. Response surface equation model, how changes in variables are affect a response of interest. Okay. So, that is a response surface model. So, we have taken a 3 variable response. So, we have used Box-Bencken model, most widely used system. Now, here the 3 variables are voltage, gun distance and toe velocity. These parameters we have seen earlier one at a time, but here in combination we have changed. The voltage with the lower value is 30 and higher level is 70 kilovolt, gun distance from 40 to 120 millimeter, and toe velocity from 1.5 meter per minute to 6.5 meter per minute, and in between at the center value we have taken, like here it is a 40, 30, 50 and 50 kilovolt. So, middle value we have taken as a third level, so 0 level. So, this is -1, +1 and 0 level we have used, and the total combination of the parameters are there. There are total 15 experiments, set of experiments. Now, we can see here the same trend we have got earlier for single variable testing, single variable experiment, but here we will get the total response surface. So, if we see here the toe velocity, with the increase in toe velocity the fiber volume fraction increases, means earlier what we have seen, with the increase in toe velocity the resin fraction reduces, it is same, it is with the increase in toe velocity fiber volume fraction increases, that means it is a reduction in resin content. Okay. But the advantage of this response surface means we can get within this experimental zone the rate, the trend of the parameter at different level, like at 30 voltage the rate of change of say volume fraction with the increase in toe velocity is higher than at 70 kilovolt. At the 70 kilovolt, if we keep the voltage here and we change the toe velocity here, the rate of increase in fiber volume fraction is lower. Similarly, if we see here at higher level of toe velocity, the effect of voltage, okay, effect of charging is higher than, it is prominent, it is significant, but at lower level of toe velocity the charge effect is not that significant, it is almost horizontal, okay. There is no change. So, here by having the response surface equation we can get the trend, total trend of experiments or of the parameters in this experimental zone. So, similarly, here this response surface shows the effect of toe velocity and gun distance on fiber volume fraction. So, this it is showing like with the as we increase the gun distance here it is changing. So, we can do this we can optimize the parameters depending on our use. Now, what we have seen in our experimental setup, we can optimize the parameters. We have seen the different factors which affect the resin content. Now, we will see the influence of various forms of polypropylene matrix on flexural strength of carbon polypropylene composite. Now, we will come to the composite making. So, the matrix formation here, the polypropylene matrix are in the form of fiber, in the form of powder and in the form of film. So, when we will use the fiber, we will form the hybrid yarn. Hybrid yarn will form. So, fiber and hybrid yarn we have to form. So, polypropylene fiber you have to use and carbon tow we have to use. So, in this case polypropylene staple fiber we will use. So, for that what we have done, we have used the drape friction spinning, where polypropylene fiber staple fibers were taken and polypropylene staple fibers were wrapped around the carbon filament, and powder we will be using the whatever we have explained, the powder coating system is used, and film stacking we will take the polypropylene film and the stacking will be done. So, this is the carbon filament and polypropylene will be stacked on that in this fashion. So, that is how we will see, and this three different types of structure, how this structure affect the flexural property of the composite. So, electrostatic spray coating when we will use as a powder, drapes free spinning when we will as polypropylene matrix as fiber, and film stacking as film method. Okay. Composite laminate process. So, we will make the composite laminate laminate. So, the total plan of work is that first drape spinning we will be doing for using a fiber as a fiber, polypropylene as a fiber, film stacking and powder coating, the drape spun hybrid yarn, powder coated trope rag, then film stacking will be done. So, film stacking on the directly on the carbon tow, then we will form the laminate, okay, and laminate of drape spun yarn, film stacked laminate and lamination from the toe frag, powder coated toe frag. Then compression molding will be done to form the composite. So, from drape we will make the unidirectional composite, that means the filaments will be or yarns will be at parallel unidirectional, where the carbon filaments will be along the axis, okay, parallel to the axis. When it is made from drape spinning, so it is called UDC. When it is made from the film stacking, UDCF, and powder coating, UDCP. And then we will study their mechanical characteristics and matrix distribution. Mechanical characteristics will be done using the flexural property, interlaminar shear strength, and matrix distribution will be done using the scanning electron microscope and microcomputed tomography. This is the total experimental plan. Material, the same material we will be using here, the carbon fiber 7 micron diameter, and for drape spinning polypropylene fiber as a sheath we will be using on the carbon fiber for producing drape spun hybrid yarn, and for powder coating as same powder coated coating principle we will be using with a cryogenically ground polypropylene powder, and film grade polypropylene granules were used to manufacture film of certain thickness, okay, for film stacking method. So, hybrid yarn production here, it is a drape yarn drape 3 system is used here, carbon toe, and drafting unit 1 the polypropylene staple fibers are used here, and it is getting opened here by using a carding drum, and the for core we will be using here the carbon toe, and the drafting unit 2 is not used as a drafting system here. At the from the front roller it is just fed here, and the fibers, staple fibers are wrapped around the surface of the carbon toe, and finally the hybrid yarn is taken, it is wound on this package. Okay. Let us see the process here. This is the drape spinning process to form the hybrid yarn. This is the carbon toe, here it is going to the drafting unit 2 at the front roller, from the front roller it is used, it is entering in the, and finally it is a wrapped here polypropylene wrapped hybrid yarn is, and this is the sliver, this is a sliver, it is going to the drafting unit, and finally we get the hybrid yarn. So, these are the different parameters used, and this pictures we have already explained in detail, the schematic of the spray coating where we get the powder coated toe frag. These are the parameters which have been used in the powder coating. Voltage 40 volt we have used here, conveying air pressure 1.5 bar, fluidizing pressure 0.5 bar, the distance of the gun from the toe 40 millimeter, toe velocity 3 meter per minute, oven temperature 190 to keep the flexibility intact. Otherwise, at 200 and 220 we have seen at that temperature flexibility reduces, ultimately that finally we have to use this powder coated toe brake for weaving. Dosing air pressure 0.4 bar and tension 160 centinewton. And for film stacking, this is the carbon toe, this is a blue color, it is carbon toe, and alternatively the one carbon toe layer and one film layer we have used. And consolidation method and mechanical characterization. So, this is the consolidation method, means here we have made the composite, okay. The after wrapping a number of layer, here in the compression molding machine is used with a breathing pressure of 8 bar, curing pressure of 10 bar and temperature of curing is 190 degree Celsius. And these are the molds, one is male female molds are there, and this is pressed against each other. In between that there is a toe brake is there. So, compression molding was used to consolidate the composite. Okay. So, this we have the mold comprises of a female and a male part, okay, and a cavity between them. So, toe brake was compressed at 10 bar pressure for 10 minutes. The composite were then cooled at 100 degree Celsius without removal of pressure. So, pressure was kept, and final dimension of the composite was 20 millimeter in width, 160 millimeter in length and 3.2 millimeter approximately, it is a plus minus 0.2 millimeter thickness. Okay. And what we have done? We have prepared the unidirectional composite, and these are the parameters of unidirectional composite. So, with PP fiber, what we have used polypropylene fiber 2.5 denier polypropylene staple fiber we have used, and as a matrix here, and carbon reinforcement for all 3 samples where carbon toe was used. So, and preformed structure is a drape spun hybridian as we have seen here, and then for stack making. So, stacking before consolidation where 8 layers were there with 14 number of turns. So, there are turns we have seen, this is a plate suppose, and there is a turn, 1 turn means 1 layer, such 14 turns will be there. Okay. These are the 14 turns and such 8 layers will be there. Like 8 layers, then it is this total system, the total material is put under the compression molding and we get the compression molded composite. Okay. And as it is made from drape, so that is why UDCD. Similarly, carbon toe powder similarly 8 layer and 14 turns. So, UDCP. So, unidirectional composite made from powder coating, and for PP film it is a one film we have taken, it is a 50 micron thickness with carbon toe is there, and in this case here 8 layer of 14 turn was there, but in between there were the films were there. Okay. UDC F. And the testing what we have done for the 3-point bending testing, okay, with this parameters where crosshead speed is 5 millimeter per minute, and at the same time it is a short beam test which is shown here, short beam test. So, to get the flexural characteristics of the composites, and we have done a detailed study for all these composites made from drape spun hybrid yarn, from film stacking and powders coating, and we have compared their result, and that all these results we will discuss in the next class. Till then, thank you.